Okay, so today we're going to discuss control charts, and some of you may have heard of this term, or maybe even been on the control chart bandwagon where somebody says, "Oh, we need to start control charting all our processes," and somebody always asks, "Well, what is a control chart?" So this is just going to be kind of a easy, gentle introduction into control charts and kind of how they work and what they could be useful for. So what I've done is I've developed a process. It's a fictional process, and it's called the coin toss process. And it's basically taking a fair coin. So fair means equal probability of heads and tails, flipping it 100 times, and then counting how many heads I get. Okay, we don't need to count how many tails we get because each time we're flipping it 100 times, if we know how many heads we get, we can simply figure out the tails with simple subtraction. And basically, I've graphed this process over time. So for example, this first data point here represents how many heads I got out of those 100 coin tosses. So it looks like I got about, I'd say about 43. Now I'm going to do the process again, and looks like maybe I got this time 48. And do it again, looks like maybe 61 or 62. Flip it another 100 times, and oh wow, look at this, got 50 heads right there. Now, with a fair coin, you would expect, 50 heads, 50 tails, but in reality, there's always going to be some kind of variability. And this graph kind of shows that variability over time. So this is the first step in the development of a control chart, graphing some kind of output as a time series. And we do that, and along with this chart, we also have another chart called a moving range chart. And what this does, it actually takes two data points, okay, calculates the difference, and then plots that as a data point. And then I'll do it again for this set here, okay, and I'll graph it. So the purpose of a moving range chart is to provide an estimate of the system variability. And if you take the average of all these moving ranges, you get 6.72. So what that says is that there's approximately a difference on average of 7 heads between different trials. Okay, this will be useful in calculating what are called the control limits. So it provides an estimate of the variability, and there are simple formulas out there to convert it to control limits, which was done up here. So another aspect of a control chart is building these control limits. So these represent the natural variability of the process. So this is usually constructed at plus or minus 3 standard deviations, which is a little bit more than 99% of the data values, and it's saying that you should get between about 69 and 33 heads 99% of the time or so on a coin flip of 100 coin flips. Okay, and then another aspect is also calculating the average of all these points, and if you do that, you get 50, about 50. So this corresponds again to what we would expect to see long term of a fair coin of getting 50 heads and 50 tails. Okay, it's about 50, 51 here. And just by visual inspection, the center line here is the 50 mark. You can see that about half the points are above and half are below. Now, this is essentially the anatomy of a control chart. So you have the time series, you have a center line, you have the upper and lower control limits, kind of based on the natural variability of the process. Well, how could this be useful? Well, what's useful here, it's actually define the variability of the system. So let's say, for example, there was a data point, let's say this one here. Instead of being there, it was actually way up here, okay? So maybe you were getting, on one trial of 100, one outcome of 100 flips, you got 100 heads, okay? Basically, this point would be well outside what would normally be expected for this process if it was in a state of what's called statistical control. So let's say you did get 100 heads out of 100 trials. Yes, this could happen by chance alone, but the odds are so minuscule that it's more worthwhile to look at if there's actually an assignable cause. So a lot of this data, you see the variability here is what's called common cause variation. And then the stuff out here that's well beyond the fences here is actually called, the assignable cause variation. Okay, there's something probably else that's going on here. Just one point of clarification too is these control limits are not specification limits. So a lot of times people get spec limits confused with control limits. Control limits are based on the variability of the process, okay, as it's running. Specification limits are usually associated with some kind of requirement, and those are used more for capability analysis. So if we have a requirement out there, we could use the variability of this data set and calculate what's called a capability index to see how well we're conforming to some kind of requirement. This is also very useful in making decisions. So for example, in the business world, I know a lot of times they might take one data point and compare it to the last data point and call it good or bad. Well, that's pretty poor decision making because you really have to understand or provide a context for your data. Okay. So another example would be, let's say this is consumer complaint data and you're a manager or something and you're looking and you see this trend over a few months and everything's going down, and you report to your boss, hey, things are going great, consumer complaints are trending down, and then all of a sudden over the next few months, wow, they start going back up and it's like we don't know what happened, the system might be going haywire, and everybody gets excited and all this kind of circus going on, when in reality this is actually just part of the same system of variability. There are going to be ups and downs in a process, even a process that's predictable in a state of what's called statistical control. There is going to be this variation. So that's how this is useful in the decision making process. Now let's say, for example, you had this situation where you had the process from before, it looked pretty good, and then all of a sudden you see this gigantic drop. So now you have a process level shift. Okay, it doesn't take a statistician to see that something changed here, and you can even see it in the range chart. Okay, so the range chart has a control limit as well, okay, for the variability component, and you can see that it looks like on average maybe you're running about 20 heads per 100 trials. Okay, so definitely something has shifted here. This is pretty unusual, and this is where you'd want to start to investigate. Okay, maybe somebody passed you a counterfeit coin or a trick coin or something like that. So here you definitely want to look for some kind of assignable cause. Now, this could be a good thing. If this was a consumer complaint data set, you might have had a huge process shift, and maybe it was a result of, let's say, some continuous improvement efforts. And you can go to your boss and say, hey, look what we've done here. We've had a process shift. If this was sales data, this would probably not be a good process shift, because you're in a state of losing some kind of revenue here. So again, this is how these things work, and these have been around for quite some time. They were developed in the 1920s by a guy named Walter Shewhart from Bell Labs, and they're kind of a fundamental piece of the quality practitioner's toolbox. And over the years they've evolved. They also have sensitizing rules. In the old days it was kind of like, well, if you have a point outside the control limits, something's gone wrong. But now they even have more rules to look for finer detail in the data itself. It's called sensitizing rules. And there are different types of control charts. Like I said, they've evolved, and they apply to many different situations. And if you're a control chart purist, for example, you might have said, well, why didn't you use a binomial chart here? Which I could have, but since each of these trials represented 100 coin flips each time, and the value isn't close to zero for the amount of heads, this is a pretty darn good approximation for this particular process here. But there's lots of materials out there on this. A lot of stat packages do it. A lot of these formulas are very simple. You can implement them in other software packages. This is what's called an individuals chart, but some charts are also based on subgroup averages, where you take maybe 4 or 5 pieces of something and then average them and then plot the data point there. So again, a lot of resources out there. I hope this kind of helps a little bit, and you can certainly further your investigation by reading up on it some more. Okay, that's it, and we'll talk to you again.